The first term that we're going to talk about in this section is the term determinant. We're going to start with just a 2 by 2. A determinant of a 2 by 2 matrix is the difference of the products of the major and the minor diagonals. We learned how to do this because this actually helps us solve systems of equations. So last chapter we solved systems of equations by graphing or by substitution or by elimination. And matrices is another way to solve systems of equations. And one of the ways that you solve them is using this thing called a determinant. So the major and the minor diagonal, the major diagonal is this guy at the top left to the bottom right. You see they labeled it A, B, C, and D. If you multiply A and D, that is your first diagonal. For the determinant for a 2 by 2, you always subtract. And then you multiply the other diagonal, C and B. All right, very simple process to find a determinant for a 2 by 2. So let's look at this first example, example number 1. All right, they want us to find the determinant of this 2 by 2 matrix. I do want to point out the notation. You'll notice that it doesn't actually say find the determinant, but your matrix no longer has the little lines on the top and the bottom. Okay, so when we drew our matrix before, it had a little cap on the top and the bottom that goes in. Now it looks almost like an absolute value sign where it's just a straight stick with no cap on the end. That automatically means that you are finding the determinant. When they take those little caps off the top and bottom, it means find the determinant. All right, so if I wanted to find this, I'm going to take my first diagonal. So that would be the 3 and the 4, and I would multiply them. So I would say 3 times 4. Always subtract, always subtract. And then you are going to subtract the other diagonal, the 2 times the 5. So 3 times 4, that gives us 12. 2 times 5 gives us 10. The determinant here is 2. That's all you do to find the determinant of a 2 by 2. All right, so I want y'all to try a couple of these. There are actually 2 ways to do a 3 by 3. I find that students really gravitate to one way or the other. So I'm going to show you both ways. Your book actually only shows you this way. So I'm going to show you a way that's not in your book as well. All right. So the first way is to do 3 diagonals, but you kind of have to draw the other ones out. And by that, I mean they have A, E, I, and you multiply those, plus B, C, and then you jump over here to G. So when you're doing it this way, I actually recommend that you take this matrix and you take these first 2 and stick them over here, right? And that'll help you with your diagonals that you need to be able to do it correctly. So what you're really doing here is you are taking the 3 diagonals that you can get from that top row. So multiply A, E, and I, plus B, F, and G, plus C, D, and H. That's your first group. All right. And then you are going to subtract from that your diagonals that go bottom left to top right. So now we're going to subtract, and you notice that it's grouped. You want to do those additions first. So you're going to take the G, E, C, that's this guy, H, F, and A, and I, D, B, and subtract him. All right. That is your 3 by 3 diagonal. So you do all 3 diagonals and subtract all 3 from the bottom. All right. There's another way to do it. You can do it with 2 by 2s, and I'm going to show you that one. All right. You pick a row. So let's say they picked this row, and you start with this first guy. You multiply him by the 2 by 2 that's left, minus the middle guy multiplied by the 2 by 2 that's left, plus the third guy multiplied by the 2 by 2 that's left. Both of them will give you the same exact one. And so it just depends on which way you like it. I will say that what they do here is they negate anything that's not on a diagonal. So if this is one of the guys multiplying, you're going to negate him. They do this weird negation depending on which one you choose. So I'll show you that when we do the example. There's two different ways to do these. You can do all three of the diagonals minus all three of the diagonals, or you can do quick 2x2s. Sometimes this way is easier if you have some zeros in there that'll zero out your 2x2s, but we'll look at both ways. So let's look at this 3x3. All right. So if I take this and I use my 3 diagonals, what I'm going to do is I'm going to take my entire matrix, I'm going to duplicate those first 2 rows and put them at the end, and then I'm going to do some diagonals. So I'm going to say in here, I'm going to multiply my first diagonal, which is 2, 3, and 6. So I'm going to say 2 times 3 times 6, okay? And I'm going to add to that the next diagonal, which is 1, 4, 7. So 1 times 4 times 7, plus the third one, 3 times 5 times 2. Okay, that's my first one. And then I am going to always subtract, and I'm going to do the next one. And I'm going to go the opposite direction. So I'm going to start at the bottom, 7 times 3 times 3, plus 2 times 4 times 2, plus 6 times 5 times 1. All right, that's my first way of doing it. So I can, oh, it's not going to let me do all those. I can add them all up, multiply, and get my 3x3 determinant here. All right. Questions on setting that one up. And then you just do your multiplication. So I'm just going to actually do it out. So I have 2 times 3 times 6, that's 36. 1, 4, and 7 is 28. And 3, 5, and 2, that's 30. All right, so I add those up, and I'm going to get 94. Then do these. 7 times 3 times 3. 2 times 4 times 2. And 6 times 5 times 1. Add those up, and I'm going to get 109. 109. And then remember, we're subtracting. All right, 94 minus 109 is negative 115. So not a ton of big numbers or anything like that. You just have to remember what you do with your diagonals, all right? And then I'm going to show you one more way to do this. So I'm going to do it the other way, and we'll see, we should get the same exact thing. All right, so if I take this guy, and I want to get it the other way, we're using my 2x2s. Then I would just do, if we take this first row here, then I would say 2 times the 2x2 that's left. So that's times 3 times 6, my 2x2, right? Minus 2x4. All right, that's my first diagonal. Minus 1. And then I'm going to look at the next 2x2 that's left over. If I use this 1 and ignore these, it's going to be this guy and this guy. So I'll say 5 times 6 minus 7 times 4. And then plus my 3, my leftover 3. 3, and I'm going to use this 2x2. 5 times 2 minus 7 times 3. And then I just calculate. So I have 18 minus 8. 2 times 10 is 20. We have 30 minus 28 minus 2. Plus we have 10 minus 21, that's negative 11, so minus 33. Right. So I have 18 and negative 33, which gives me negative 15. So you can do 2x2s, or All right, let's look at the first one. So if you did it using your diagonals, then your first one would be 9 times 5 times 1 plus 8, 4, and 3 plus 7, 6, and 2. All right, you take that group and you are going to subtract your second group, which goes this way, 3, 5, and 7. Two, 4, and actually 9. Scooted in too close. 1, 6, and 8. All right. And then we're just going to do these. 9 times 5, 45 times 1 is 45. 8 times 4 times 3, which is 96. 7 times 6 times 2, which is 84. All right, and then we have 3 times 5 times 7. Right. Yeah. 2 times 4 times 9, 72, 48. All right. Then you need to add them, which is, there we go, 225. This is the second way. You're going to take the -3 and do the 2 by 2 for this guy. So you're going to do the 2 by 2 for the 1, 8, 4, -2. And then you have -0. It actually doesn't matter what's in there because the next guy is a 0. So you can just ignore that middle one. This is actually how I would do this one because of that 0. And then plus you have the 5, and you're going to multiply it by the 2 by 2 that's left over when you get rid of the row and column of the 5, which is 2174. And so when you do this guy, you would say 3 times 1 times -2 is -2, minus 4 times 8 is 32. This zeroes out, plus 5 times 2 times 4, which is 8, 7 times 1, which is 7. And so you have -2 minus your 32, which is -34, and then plus 5. Helps to put your negative there. Cramer's rule. He was a Swiss mathematician in the 1700s. He's credited with this particular method of solving systems of equations. There's a lot of words here. I'm going to kind of explain what you do. You get your overall 2 by 2 determinant of a system of equation. And this is for a 2 by 2 specifically, but you can do it with a 3 by 3 as well. And then you replace a column with your answers and get another 2 by 2, and replace a second column with your answers and get another 2 by 2, and then you divide them. And so for a systems of equations that just has an x and y, it's a pretty fast process for finding your x and y answer. And so we're going to do this method, and then we're going to compare it to the other methods that we've learned. So this wants us to solve the system using Cramer's rule. The first thing you're going to do is you're going to set up a determinant for your 2 by 2 that is made up of your coefficients. Okay, so this is your coefficient determinant. And so we're just going to label it here. And we want the determinant of what would be made up if we got all of our coefficients. So the 4 and the 3 and the 6 and the -1. All right, so all I did was pull my coefficients. Does everybody see where I got those numbers from? Just the coefficients of my xy, xy. All right? So you do want it in standard form, so it needs to be xy equals a number, right? And then you're just grabbing your coefficients, 4, 3, 6, -1. And then I am just going to do a 2 by 2 determinant here. So I'm going to say 4 times -1, that's my first diagonal, minus 6 times 3. 4 times -1 is -4. 6 times 3 is 18. So -4 minus 18 gives me a determinant of -22. So I'm just going to set him aside. That's my first determinant that I'm going to find. And then I am going to take this guy and I'm going to find an x determinant. Okay? When you're doing matrices, your columns really go in order. So your first column represents your x, and you can see that, right? This is your x column. Everybody see that? Because those are my two x's. They're lined up. The second column is my y column. All right, so I'm going to replace my x column here with my answers. All right, and I'm going to do another 2 by 2. So instead of writing 4 and 6 right here, I'm going to write 8 and 1. And then I'm going to leave my y column alone. So I'm going to say 3, negative 1. All right, so all I did was replace my x column with my answers, 8 and 1. I replaced my x column with this guy. Everybody see? Now I'm just going to do a 2 by 2 determinant. So I'm going to say 8 times negative 1 minus 1 times 3. So negative 8 minus 3 gives me negative 11. All right? Then I'm going to do the same exact thing with my y column. So now I'm going to take this guy, my original. I'm going to leave my x column alone. And I'm going to replace my y column with an 8 and a 1. And now I'm going to do another determinant. 4 times 1 minus 6 times 8. So that gives me 4 minus 48, negative 44. Okay, so I have a coefficient determinant, I have an x determinant, and a y determinant. Okay? And Cramer's rule says that if I take my x determinant and divide it by my coefficients, I will get what x equals. So x is going to equal what happens when I take my x determinant, negative 11, divided by negative 22. So that means x is going to equal 1/2. Negative 11 over negative 22. My y is going to equal what happens when I take my y determinant divided by my coefficient determinant, negative 44 divided by negative 22, y equals 2. This tells me the coordinates 1/2, 2 would be the answer to this. Those would be my coordinates, okay? Now I could solve this another method. I could solve this by elimination. I could multiply this second guy by 3 and add down. That would eliminate my y's, right? That would let me solve for x. Then I could plug my x back in and solve for y. All right, and if you did that, you would get positive 1/2, positive 2 as your x and y. You could solve by substitution. You could subtract the 6x over, divide by negative 1, and plug it in. And then you could solve for x. X would be 1/2, plug it in, and you would get a y. You can also check these. You could plug in a 1/2 and a 2 and make sure that you got the right answers. So you could say, okay, 4 times 1/2 plus 3 times 2 equals 8. Yeah, 2 plus 6 equals 8. That's right. 6 times 1/2 minus 2 equals 1. Well, that's 3 minus 2 equals 1. Yes, 1/2 and 2 work for both of those equations. So you can use this method using a 3 by 3. You would find your determinant of your coefficients, 1, 1, 2, 2, negative 4, 2, and negative 1, 1, and 1. You would find a 3 by 3. Then you would replace the first column with this and find an x. Replace the second column with this and find a y. Replace the third column with this and find a z. Then you would do the same thing. Your x divided by your coefficient, your y divided by your coefficient, your z divided by your coefficient. So you can do a 3 by 3 using Cramer's rule. You just have to do 3 by 3 coefficients, right? And me personally, now if I were solving this because it's set up so pretty, I would probably use elimination here, right? Because I already have a -1, a +1, and a +1 in my z. But it's possible, especially if you have larger numbers and using elimination is going to be a little more difficult. With matrices, you're really just multiplying and subtracting, and so you don't have to worry about it quite as much. So this is a really cool concept here with matrices. Determinants can also be used to find the area of a triangle. Irregularly shaped areas can be estimated by breaking the region down into triangles. But what they've done is they've done an X row and a Y row, and then they've done a row with all ones to do a 3 by 3, because triangles obviously have 3 vertices, okay? And so they just did the x1, y1, x2, y2, x3, y3, and then they've done a determinant. And then once they take the determinant, they multiply by either positive or negative 1/2. Here's the thing. The reason it's positive or negative is because area is always positive. So if your determinant is positive, you're going to just divide by 2. If your determinant is negative, you're going to divide by -2, because your area of a triangle must always be positive. And so if I were to do this one, I would just set up a 3 by 3. My x's are -3, and my y is 1. My x here is 1, my y is 3. My x here is 2, my y is 1. All right, so I have my 3 x's and y's, and then my bottom row is always going to be a 1. Now, personally, I would do the 2 by 2 method here because I have 1's in front of it. And so if I were going to do this, I would actually choose this row and I would do 2 by 2's. So I would say this 1 times the 2 by 2 that's left over. So you ignore this row and column, and I'm going to do the 2 by 2, 1, 2, 3, 1, minus this one and the 2 by 2 that's left over. So that's -3, 1, 2, 1, plus this guy, 1 times the 2 by 2 that's left over, -3, 1, 1, 3. So I would actually do it this way. You're welcome to do it by the diagonals to find that determinant. All right, and so I just have 1 minus 6, or -5, minus -3 minus 2, minus a -5, and then plus a -9 minus 1, which is -10. All right, so this ends up being -10, and I need to multiply by either positive or -1/2. Well, my area has to be positive, so I'm going to divide this by the -2. My area here is 5 units. All right, so your triangles, you can find your area by finding the determinant and multiplying, or rather dividing by either positive or -2, depending on whether your determinant was positive or negative. But you are welcome to always do the diagonal method. I just choose this method when I have all 1's, because I can do 3 quick 2 by 2's when I do it. But you can shift it over and you can do your diagonals if you want to. I do want you to try one of these.